Hello, everybody, and thank you for taking the time to come and listen to this. So, yeah, my name is Frederick, and today I'm going to tell you a little bit about Teton and our mission towards building an AI nurse. My name is Frederick, and I did my bachelor, master, and PhD here. During my PhD, I was at UC Berkeley and also at Meta for a while. And now I'm part of the AI team at Teton. And without further ado, kind of the three things I'm going to talk about is our current product, our a bit more deep dive into how our AI model works, and lastly, I'm going to talk about some of the directions I find super interesting going forward. So, what is Teton? So Teton is a Danish startup, was founded in 2020 by Mikkel and Esben, and we're building this AI assistant that can help medical staff with their day-to-day work. So what we are providing right now is this overview, as you see over here. So you have a mobile app where you can see what all your patients are up to. If they are sitting in the bed, if they're sleeping, if they had a fall, etc. This is super useful for medical staff because they can prioritize their day, figure out if they need to attend some patient or not. For example, if a patient is sleeping, they probably don't want to wake the patient up. So we have deployed this across multiple sites in Denmark, Switzerland, and the UK, and soon in the US. And this product has shown to be super, super efficient. One of the numbers we're super proud of is that we have reduced the reaction time. So that's after a fall happens, how long a patient lays on the floor, from an average in a Danish site for about 2 hours to a couple of minutes. We can also, with this product, reduce the number of falls. So the nurses, they know which patients are in risk of falling, and they can put these patients at high risk. And as soon as they sit up in the bed and are about to get out, the nurses can get an alarm, and they can come help the patients before a fall actually happens. So how does it actually work? So what we do is that we install a camera in the room and a computer. The camera sends a live stream to the computer where an AI model runs that detects what's going on in the room and then deletes the image. So the footage never leaves the room. Everything is processed locally. And the only thing that leaves the room is the detections from the AI model. So what can a model see? It can understand kind of all the static objects in the room, such as the bed and the chairs, the wheelchairs, etc. Can understand where people are in the room and what they're doing, if they're laying in bed, sitting in a chair, or walking around. And then we can detect falls. And when a fall happens, the nurses will get a notification or an alarm on their phone so they can come help the patient. So yeah, in short, kind of what we provide is this product that gives alarms. We give an overview for nurses, and we also provide more insightful stats, health stats for each patient. So I said like an alarm is sent out when somebody falls, but also what we do is that we generate these anonymized fall animations. So this is a direct output of our model, and this is super, super useful for health staff because you can see what's actually going on in the fall. And a lot of our patients have dementia, so they can't really remember exactly how they fell. But this way, the nurses, they can assess if the patient hit their head or were severely injured and need to be hospitalized or not. Furthermore, they can use it as a preventive measure to figure out if they need to remove or move something that can prevent future falls. This is like a complete anonymized representation where you don't see any facial features, you don't see pictures on the wall, but you still see kind of the geometry of the room. So I was saying we also provide health stats about patients and kind of can monitor how they're doing. So these are stats from 2 different patients, but one, we measure the patient respiration, and all of this is done from our vision model. So here in the first widget, you can kind of see that the respiration is in the typical range until very recently, where it dropped a little bit. We can also analyze how the patient has been sleeping, if they've been in a calm sleep, how many hours, or if they've been in a restless sleep. And these data can help nurses take informed decision about which patient they need to attend to, or which patient are doing like just fine. Lastly, we have built this data platform that provides an aggregate overview for decision makers and leaders to take informed decisions about what's going on in a site. Are we doing all right? Are our patients sleeping well? Are we kind of having the right trends in our number of falls or reaction time and so on? So these are kind of the tools we're building to kind of both help patients, care staff, and leaders to take informed decisions. So next, I want to talk a bit about our AI model and how all of this works behind the scene. So our AI model is called FEAR1, and it's a multimodal, or no, HydraNet model that predicts multiple things and have like a shared backbone. So it takes an image as input, and then it processes that and predicts multiple things. So one is bounding boxes of static objects and dynamic objects, as you see here. For each dynamic object, we predict the skeleton pose and the action that the person is performing. So if it's like person is laying on the ground, sitting in a chair, or walking around. Furthermore, we predict this semantic segmentation map. So for each pixel, we classify if the pixel belongs to the floor, the wall, the person, or the bed. And furthermore, we predict monocular depth, so how far away is each pixel from the camera. This is super, so here in this visualization, red is further away and more bluish is closer. So this gives like a very rich understanding of what's going on in the room. And that can be used for many things. We can make this point cloud representation from a single image. We can project all the pixels into 3D, and we can then render the room from novel views. We can do that with our semantics as well, so we can see how the bed is moving over time. It can also be, we combine these two also to create the fall animations that I showed before. And then I think maybe one of the coolest application of this spatial intelligence is this scenario. So take some time to explain what's going on here. So this is a site where we have two cameras connected to the same device. So you see there's one camera that has a green border that correspond. So you need to, the visualization on the right is kind of a top-down view. So what you see is the floor plan. So we can detect the floor in each view. We can calibrate the two views so we know where the cameras are relative to each other. And then we can basically see the entire room from above. Hope this visualization makes sense. So what I want to show you now is that I start the video, and in the top view, a person is detected in the bathroom. You will see him here. And what you see is that we predict the person's feet onto the floor. So you can see he's inside this polygon, and you can see how our detections are shown here and how he is projected onto this floor plan and how his movement corresponds to his position. And you can see he's now detected in the second view, and you can see how he's moving into the floor plan of the second view. So why do all this tracking in 3D instead of doing it in a 2D space? First of all, it's way easier because assumptions about constant velocity and so on holds way better in like a metric space than they do in this very distorted fisheye space. And second, it allows us to use this calibrated setup to keep the same track across views. The second kind of application I want to focus on is how we do respiration, which is another super cool thing we can do from just the camera. So basically what we do is that we use the skeleton pose I showed you before to locate the chest area of the patient. And on the chest area, we put this grid, which is visualized here. And then we use an algorithm called optical flow to track how points are moving across time. And from that, and some clever signal processing, we can extract this signal. And by detecting the peaks and valleys of this signal, we can compute a breathing rate. So this is Andreas from our office who is testing the algorithm. And he's a healthy young man, so the respiration signal is super nice and repetitive. We have like another example here where you see, again, it's very repetitive in the beginning, but then suddenly breathing stops. So the points are suddenly not moving anymore. And then after a few seconds, it starts again, as you will see here. So this is like a phenomenon called sleep apnea, which is possible to detect with algorithms like this. So that was a bit about kind of some of the technology behind our product. And lastly, I want to kind of talk a bit about what we have in the pipeline and what we're working on now. So we're working, like there was an announcement here in the fall that this new supercluster has opened called Gefion, which is enormous. It's more than 1,500 H100 GPUs. It's ranked 21st in the top 500 list. And it's a huge cluster funded by the Novo Nordisk Foundation and IFO. And we won among, like, I think the 6 company early access to this cluster. So we will get like enormous amount of compute available. And we're going to use this to train TU2, the follow-up of our first model. And it's going to be different in 2 ways. First of all, TU1 is a frame-based model, so it predicts everything independent of the previous frame. It does so each frame is independent, and it's trained in a supervised setting. So we have like ground truth labels always. What we want to do is have a video model that understands its previous predictions and what's previously happened, and uses that to make predictions for the current time step. And also we want to use unsupervised pre-training, which allows us to scale up to our model to see way more data. So I'm going to zoom in on these 2 kind of approaches and kind of tell a bit more about how it works. So as I said, this is our current model. It's a network that predicts these 3 outputs, as I said, and everything is independent over time. So what we will do is kind of enable a memory so you know what just has happened. So this will enable like smoother predictions. It will allow you to understand more long-term actions. And it will enable you to distinguish better between patients and staff. So for example, elderly people walk in a very different way as young people and so on. And these kind of cues are only visible if you have like some temporal knowledge. But it takes a lot of data to train this type of model. And what we want to do is to use something called mask autoencoding, which is kind of the analog for pre-training in LLMs, where in LLMs you use next token prediction, which allows you to learn kind of the semantic structure about languages without having like expensive human annotations. The analog in vision is that you mask out regions in the image and you then ask the network to infill the missing parts. So this objective allows you to learn, or the network is required to learn which pixels move and which ones are stationary, which ones move together and which ones don't move together. And this will give like really rich general features that understands how the environment looks like and what's going on in the scene, which can then be fine-tuned for downstream tasks such as action recognition, gait analysis, pressure ulcer detection, and so on. So, I mean, this was a little bit about our company, what our AI does behind the scene, and kind of some of the very exciting things we have in the pipeline. Yeah, and if you have any questions, or if you're looking for a job, or if you're looking for student projects, we're always very happy to collaborate. So yeah, please reach out to me on this email if you wanna collaborate on something. Thank you for your time, and if you have any questions, please yeah.
Thank you so much. I see we have questions.
Hey, Frederik. Great presentation. You mentioned that the space you're operating in is sort of sensitive. Recording data in the homes of people or at hospitals is very sensitive. That gets me curious, though, because like you're developing your own models. How have you done data collection for this, and what data sets are you basing this on?
Yeah, I mean, it's a great question. So when we started out, kind of the first thing was to do these data heists, where we basically dressed up as patients and staff, and we acted as we were falling, or we were doing all sorts of actions. And this can take you pretty far. And we also do that if the model is not performing well. We do a data heist where we kind of lay on the floor in a specific room and so on. But surprisingly, people, so like the alternative to that is to ask people for consent to monitor if they're going on, what's going on in the room, and then collect some data once in a while. So we ask patients for consent, and then if the model is unsure, we like grab a video snippet and use that for annotation and improving the model. But yeah, the default is no data leaves the room. But yeah, in case we have consent, we collect some data.
All right. Follow-up question then. Are you guys using synthetic data?
We are to a certain degree. So we are using some models that's trained on synthetic data. So I mean, there's a lot of depth models out there now that's trained on synthetic data that we are kind of leveraging. Yeah, to that degree, but otherwise not, no.
Well, I have plenty more questions, but I'll hand the mic to somebody else.
Thank you. Great presentation. A couple of questions, but so you're generating those content based on only the data that you get from the video that's being stored on the local. So nothing transferred to your servers as a video file. It's just pure detection, text, and that. And did you try to see how accurate those data are, like the projection that you build versus the reality?
Yeah. So I mean, we both have like an in-house data set where we evaluate all our algorithms, but we also have metrics from production. So there's like a feedback loop in the app where staff can annotate if a prediction was correct or not, and based on that we can compute like scores from production environments as well. Yeah.
Can I know after a couple of years how was the result was like? Is it accurate enough that your customers can trust?
Yeah. So I mean, it's working really well, and I mean, there's some early result from various sites where you can see that there's less need for staff during the night because like currently without a system like ours, how it works is that you need to go around and check up on all your patients and do it. Usually they do it twice a night, and that takes a lot of like resources to walk around and check up on everybody. Plus, every time you do it, you end up waking up the patient. And with this system, they don't have to do as many checkups, which means that they don't need as many people working nights, especially.
But how long does it take to convince them to use it and trust the system? Because it's pretty new software and hardware as well. And those people in that environment, they are not familiar that much with the tech that they can trust. And how long does that take?
So what we do, how we implement this is that we first have the system running for a month, which we call the baseline period, where the people don't have access to the system, but it's counting number of falls and so on. Then we introduce the care staff to the system, and it runs for 2 months in this pilot phase. And then we compare the stats during that period where they had access to it with the months where they didn't have access to it. And from all the sites, we've seen a huge drop in number of falls, reaction time dropped a bunch. And also the staff is super happy because they have this overview. So it's pretty easy to convince them at that point, at least the staff on the floor.
Thank you.
Hi, thank you for your presentation. It was really nice. I was wondering about the capabilities of the model versus what a human can do, because you're saying it replaces their rounds in a way in the night, but a human can detect way more than your software can. So have you any insights on what things might occur if the model oversees something? That might be a risk, I can imagine.
Yeah, no, it's a great question. I mean, the diversity of tasks a human can do is like way more than we can do right now. And I think some tasks we can kind of help automate, and we can probably also improve what a human is capable of do. Just kind of very repetitive, boring tasks. Probably humans will make mistakes in these, where a system like ours be better at these things. But I mean, there's a lot of stuff, right? And we just provide some data for humans to perform their job. So it's like, it's definitely not replacing people. It's just kind of giving, it's like a tool for people so they have more insights on how to do their day-to-day job. I hope that kind of answers.
Hi, yeah, thank you for your presentation. Super cool. That looks like a neural radiance field there on the right. I don't know if I'm correct. I was wondering, so you had this example with the 2 cameras in different rooms, but I was just wondering why you don't put 2 cameras in the same room and then infer the depth from 2 cameras instead of just 1.
Yeah. I mean, the main reason is cost and complexity. And like, we can solve the main task with just 1. I think monocular depth is becoming really good at this point, and I don't see stereo as a need anymore.
Okay, nice.
Hi, thank you for your great presentation. So, as I've understood, the problem that Teton AI is trying to solve is the pressure that nurses are under here in Denmark, because Denmark lacks nurses. And when we think about when we think about nurses and their job, there is a huge physical aspect about it. So I was wondering if you are considering to expand into robotics, like do some of the physical tasks that the nurses have to do in their daily life.
Yeah, I think it's a great question. I don't think it's anything we have any plans about doing right now, but I think it's a good observation that it is like a very physical presence means a lot for patient recovery and so on. And actually, what we can see from our data is that staff visit patient less often, but they stay with patients for longer time. So before, without a system like this, they have to rush to the next because maybe somebody fell in another room. But with this system, they have like more time with each patient, which is really nice to see.
Thanks for the very nice presentation. I work with large language models. My question is also following up on that. How do you annotate those data? Like, do you have in-house annotators? And also, what are the matrix to convince the? But you explained with the A/B test. But I guess my analogy here is, since we have hallucinations in large language model, and there currently are not very good matrix. to talk about that. I don't know how it is in your vertical.
Yeah,
Thanks.
I mean that's a very, very good question, and I think a lot of our work actually goes into our data engine, which is how we annotate data, and we do it in multiple stages. We have some like the first stage is that we kind of pre-annotate with the current model, kind of make the best predictions. Then we have in-house annotators that goes through these predictions and kind of correct them if they're wrong. And then we have a bunch of really, really large models to enrich these human annotations. So we did all kind of optimizations to kind of make the annotation efficient. So one is that instead of annotating a bounding box around a human, we can just ask annotators to annotate a single point on the person across a small video frame, and then we train the model to take this single point annotation and predict a bounding box. Also leverage like huge models to get segmentations, depth, poses, and so on. So we have like all these specialized models along our annotation pipeline that has one job and one job only. And then we create these rich annotations that we then distill into the tier 1 model. The second question was about the so I guess the hallucination equivalent in vision is like ghost predictions or ghost detections. And I mean, we see that, and we have some logic to kind of minimize that. And we have some logic to, if that happens, if there's consent and that happens, we collect that data and put it into the pipeline. So it's like a closed loop system where we try to improve every time there's like a prediction that's off. I can hear.
Hello? Yeah, maybe a little off question, but couldn't you achieve a lot of this with microphones and sound instead?
I think
and leave actually an open room for a lot of a lot more features to add, like sound.
Yeah, I think it's like super interesting direction, and actually in the new generation of our hardware, we have microphones. And I mean, it's exciting of two reasons. Like, first of all, it will be like an upgrade to an existing product that is in most hospital and care homes, which is this two-way speaker where staff can call patients and patients can communicate back and forth. So we can kind of replace an already existing product, but we can also use it to improve. And I think they can improve each other. And I think for Anna will talk more about multimodal learning, but I see them kind of as very useful for each other. I mean, the vision features can give you information about static objects, such as a bed, which is really hard to detect from sound. But communication, aggression, all these things, way easier to detect with sound. So I think that's definitely something we will be working on in the future.
And do you consider a marketplace for LLM applications to be to be bought or sold between? Because if you have a mic in there, you can also have the translator. You can have the listen to the heartbeat. You can listen for. There's so many opportunities.
Exactly. I mean, I think that's the exciting thing about this space, that there's a lot of opportunities, and there's just a big need of innovation in this field. And we can help nurses all over the world with these things. And I think that's one of the things that I find really exciting about this space. And I mean, with the huge need for more nurses worldwide, I think it's good if we can kind of help out a bit.
So I'm changing things up a little bit here behind us. I think we should say a big thank you and give Frederik a big round of applause. He will be around, I'm told, afterwards if you have follow-up questions. So please give him a round of applause.
Thank you very much.